Hi everyone. Two more talks to go. It's good. So a little bit more about internal waves, but also mixing. It's a little hard to separate them, and taking you to travel a little bit away from the South Ocean, even further than tropics, all the way to the Arctic in this talk, because I'm particularly interested in internal waves and mixing under sea ice, and we don't have a lot of observations under Southern Ocean sea ice. I've got some nice ones from the Arctic that lead to work now in the Southern Ocean. So this is not going to work. I'll do it from here. Oh, it's not going to work from here either.
I just read.
Yes.
That's working.
So it's collaborative work. Of course, normally a bunch of people. I've put a picture here so you can see some familiar faces in the room. And that's how Philip's Petra, Pam was meant to be here, and she's in the middle. We've got also student, Steffi Libra on the left, and Ajita, who's doing a postdoc at the moment at Ajita. Up on the right there, Will Hobbs and Kurt Paulson, as well as Alex Gentile at the top, and that's the Arctic Connection. So we haven't heard too much directly about background guts yet, but basically we know that it's really important for the current system. In terms of ocean, one of the big questions that's left with the ice is how much and what controls the fluxes of the heat. Fluxes under sea ice and the ocean sea ice. And it's particularly in the Arctic context, where it actually plays a really large role. And the question is, how much is there in the Southern Ocean control from the ocean onto the sea ice directly? So starting in the Arctic, this is a really nice map from a few years back, 2021, actually just last year. The yellow line is the average minimum, and the white, the satellite picture is from what it actually was. You probably all know that sea ice in the Arctic has been retreating really, really fast, so decreasing 30% per decade since like the 1980s, and the thickness has decreased by about half. So in 2015, this institute experiment took place called the sea ice drift. So you put a ship in the ice, it freezes in, and then you drift with the sea ice, and you can observe the sea ice in its environment as it's moving around. The idea so this is called NICE 2015. This expedition was to try and have a look at this new kind of system as the Arctic is changing from a multi-year ice, so ice that survives every winter, system to a first-year ice dominated, which means that most years, most summers, a majority of the sea ice actually melts now, which means that every winter, most of the sea ice has to reform from scratch, forming first-year ice, which will melt again next summer. So we've moving away from a multi-year ice system in the Arctic to a first-year ice. And that has a lot of impact on absolutely everything, not just the thickness of the ice, but, you know, the habitat that it is. When you had multi-year ice, you also get different properties, optical properties, how much ice gets through, how much snow piles up on it, how hard the ice is, how fast it floats, drifts around. So the whole point of this expedition was to go and have a look at this new system deep in the Arctic where we rarely go. It was on the European side. So this point works. This is Norway here. Svalbard, the archipelago, and so leaving from Svalbard, went as far north as possible in late December, got frozen in, and then drifted for 6 months, all the way until summer, until early July. Different people, not the same people the whole time, very small ship, not an icebreaker, about 19 scientists only on board to cover all sciences. And the picture at the bottom is in summer, it's the ice around the ship, and we actually, had lots of little cities set up for the different sciences. So there's a little oceanography kind of patch there. I was there as the oceanographer and collected a lot of mixing observations as well as many other things. And I'll be showing some of this microstructure, so semi-direct observations of mixing in the water column under sea ice. little arrow is pointing to the tent where the microstructure was being sampled, and on ICTD was being sampled. And the map on the right shows you where we actually drifted 4 different drifts, because it turns out as we have a smaller sea ice, less thick, thinner first sea ice, it drifts faster. It's more prone to breakup. There's also more storms in the Arctic than there used to be. They travel further north now. So we had a whole lot of storms, even in winter. And the ship drifted out into the marginalized zone, into the open ocean, much faster than it would have had 30 years ago, which meant we got to do it 4 times rather than once in 6 months. And the instrument, the microstructure profiler, is this one, which we saw speak. Okay, so what we were actually looking at in terms of oceanography, front strait is the main input of heat into the Arctic through Atlantic water. So Atlantic water flows in, it's considered warm, it's anything that's above 2 degrees is warm there. It flows in following that schematic there, and it's been warming up and it's been getting shallower. So in the Arctic, you get this warm water that's pushed underneath the surface, and so it's isolated from the sea ice by upper polar waters. But this Atlantic water is getting warmer and getting shallower closer to the surface, and we wanted to look at that. Now here is kind of a time series at the same time as vertical cut of what we collected. So all the way from January until June, so we've got this 6 months there. This is mixing in color in the background. At the top, you've got the wind speed, that's storms. Every M is a storm, big M's are big storms, and in yellow, 4 that we're going to be focusing on. And then at the bottom, we've got topography, just to give you an idea. We have both deep basin and kind of shelf and plateau, and that has impact on the mixing. Yellows and colors is kind of a block background. I think I've put the mid background spatial is really low in the Arctic. It's 3.6 to -9. What else we have? Mixer depth, and mixing depth based on that kind of threshold spatial value. And what I really want you to see here is that during the storms you do have elements mixing. During the storm, a little bit after too. And the mix layer differs sometimes, and using that does, of course, but elements mixing. So we saw that we had 30 times larger values of dissipation during the storms, even in winter. And here are the vertical profiles that we have the entire 6 months. So here the profiles are separated with what we call no forcing. So we didn't have any endless wind, we didn't have any topography, because we also saw the impact of topography on mixing. In black, you have when you have both heat storm and the presence of Atlantic water close to the surface, and then in red, just storms and Atlantic water. So when you combine storms and shallow Atlantic water, we got the biggest heat fluxes right under the sea ice, which is kind of logical due to the increase of mixing close to the surface. And so during these big storms, we saw heat fluxes to the sea ice right at the ocean ice interface, about 7 times larger than the rest of the time. And so that kind of is a schematic of what happened at Atlantic water. You can see how deep it was. We were measuring mixing by rate at 250 meters. What happened in winter? So what was really interesting is that we saw this happening in winter, not just in summer. So the theory is that because the Arctic is so close and we have the scales isolating the ocean from the surface, you wouldn't really get energy going under the ice during the storms. And in winter, even if you get hot water or a little bit more heat flux, it wouldn't affect the ice. But we saw a very different picture where Atlantic water was shallow enough and mixing was enhanced enough that we got very large heat fluxes, your dissipation is degrading in temperature, right at the sea ice interface. We were working, so sea ice on average in the Arctic is now about 1.5 meters thick. So in winter it was about that much, so it's not that thick. And background heat fluxes the ocean ice interface in Africa, that's 3 watts per meter squared. So when you have 20, that's actually quite a lot. And so what happened is, after the storm, so the storm comes in, turns out it's warm, the storm in the Arctic. So in winter, we had minus 40 outside. The storm comes in, it's about 0 degrees, maybe minus 5, but it brings in rain and snow, which is very unusual. It stays there for a few hours, maybe a day, and then it's gone and it goes back to minus 40. But in the ocean, we then see some large influx, let's say, several days, and when we saw the ice melting from underneath, even though we were back at minus 40 outside, the ice is melting from underneath. And this happened repeatedly during the 6 months. So the idea is that this mixing is coming from somewhere, can see the internal waves behind. And I think this was something that really hadn't been looked at, just weren't the right observations to look at this. So I went back to some different data. We had a current ABCD, which was vessel mounted. This is again the 6 months. So we've got here the current speed in the upper 200 meters, and you can see the main storm flag in yellow again, and you can see that you have generally some larger values, not just during the storms, it's also some kind of signal when we hit the shelf or the plateau, but larger values during the storms. And if you then look at the spectra, 4 storms here. In blue, you have everything before the storm, and in red, it's during the storm. And generally, you see that the spectra is enhanced during the storm, so higher amount of energy in the reds. And then we separated cyclonic to anticyclonic, so energy that's going up and down, because the problem at that latitude is the near inertial and 12-hour frequency overlap. And so that means that we both get tide and near inertial at the same time. And what we are expecting is as we get the storm, we're generating regional waves at near inertial frequency. They will separate from the tidal signal. It's a little bit harder. So by separating it from down, we can expect that near inertial would be energy going down, whereas if you have a tidal signal, it will be going up. The good news is, for example, here you see that before the storm and the up signal during the storm, they're kind of all at the same power level, but during the storm going down, energy going down is a real peak. So that's the peak. Dimensional waves generated during the storm under SEAICE. We see this happening during nearly all the storms. These are just the nicest, but we have many storms to look at. Now, another way to look at it as well is, can we integrate the turbulent energy production in the water column during these events? They're summarized here for 1, 2, 3, 4, 5, 6 of them. Mixed layer was deepening significantly by about 20 meters during the storms, sometimes more. Integrated turbulent production was doubling, typically even 25% increase, double, tripled. So that order of magnitude increase in energy. And then we looked at the filtered velocities, 12 hours, which is around F, which is what we're interested in, because the thing that people were surprised is that, okay, maybe you get a near inertial wave generated in the mixed layer, but it's not going to travel below the mixed layer. It had some hints that it did. So here in red is the contour of the rate dissipation. And if I go to the next one, you also have the mixed layer in white. And what you see is that you've got these little blobs of red, so rate dissipation, even below the mixed layer, within a few minutes after the storms. And this happened a few times. And you end up being able to identify these vertical signals of propagating, what we think is propagating inertial waves below the mixed layer, and they're propagating at about, took about 5 days to cross the mixed layer, and that would explain the enhanced mixing after the storms and the continued melting of this gas from below within a few days after the storm. So this is a story from the Eastern Arctic. It's actually quite different in different regions of the Arctic. That's why I've put, I did put at the top Eastern Arctic key points. Over there, we do see that the change in sea ice means that we can get more energy right underneath, and there's a positive feedback mechanism where you pull up with this extra mixing heat, more heat, and have higher heat fluxes to the surface, which melts the ice, opens it more easily. It's thinner, it breaks more easily at the next storm, and you have even more input of energy during the next storm into that same area. By the time you get to the end of winter, your ice has been broken up several times, it's melted already several times, and it's more prone to even other feedback. So this is what we see in the Barents Sea and on the European side, or Eastern Arctic side. Pacific is certainly very different, and I won't go into details here, but the stratification has increased, and so you don't see any of these near-initial kind of signatures under SEAICE. So moving on to the Southern Ocean and the Antarctic, very, very different environments, very different geography, which just means that the SEAICE story is actually different. I've got some stats. I'm sure you want to look at them in a little bit more detail. I won't let them be too long because we've got a little bit of content to cover. But basically, as the Arctic has been decreasing roughly SEAICE extent and thickness, by 30% per decade, the Antarctic over the same time period, which is that way, time period, has been slowly increasing. It's not something we talk a lot about, because when you think about climate change, if you tell people that Antarctic SEAICE is increasing, you're kind of worried that people are going to sense the whole point is going to be used as a tool to say climate change doesn't exist. That's one reason we don't talk a lot about it. The other reason is it is not well understood, and long-term projections of models point to the fact that SEAICE and the Southern Ocean should be decreasing too. So there's also a lot more variability in the Southern Ocean SEAICE than in the Arctic one. There's much more of a play with atmospheric forcing. So while it was slowly increasing, and just very statistically significant for the last years, everything changed just a few years ago. So we hit a maximum SEAICE extent around 2015, the highest value we'd seen on the record, followed by an abrupt fall to below SEAICE reported with satellite data in 2016-17, which then slowly recovered. And a lot of people were saying, well, this is most likely just natural variability, we've seen a lot of it. No big deal, all right, kind of thing. And then slowly recovered, but then it just went right back down to another minima again in 2021, and it's at another record low again right now. We're probably heading for another record low for this year, which would make it 3 times in just a few years. So the big question there is, what is going on with the Southern Ocean SEAICE in terms of long-term trends? Is there a regime shift, and what is driving this? A lot of work being done in space, both from an atmospheric point of view, a little bit from an ocean point of view too. Because we do wonder how much the ocean is playing a role. Because we're already interested in collecting observations of ocean mixing under SEAICE to look at some of the dynamics we're looking at. I don't personally have any data on this right now, but working on it. One thing I would like to touch upon is recent work by student Stephanie Brown. She is looking at SEAICE predictability, and it actually touches onto this idea of mixing and stratification involved in the ocean, in the Southern Ocean. So SEAICE predictability is how much can you use current. So SEAICE extend right now to predict how much there will be over coming months. And looking at still 1 year, so the next 12 months. And the shading at the top here is correlations. So SEAICE right now with the next month's correlation is quite high, and then the correlation decreases. You lose all type of predictability over the summer, and then somehow in some places. And the idea is that as you're forming SEAICE here, you're affecting the water column, the temperature, salinity, and density profile, and you're actually storing some of the information about how much gas you produce down at depths. During summer, as you have the melt season, the enhanced stratification isolates that ocean memory signal peak, and nothing happens. But as you start forming scales again, you reopen the communication between that signal, which is not that big. There's no scale here. We're talking the top 100 meters, and whatever has been stored down there in terms of memory comes back up to this. I don't really have a lot of time to go more on this, but if you're interested, and I know people in the room argue these kind of things, this is quite neat. And it points to the fact that you do have this, not one way, but of course 2 ways, memory and the role of mixing into an ocean, into this nice predictability of the future. SEAICE extent. Now, I'll step away from this case story because what I do have is evolution, right? It's not on SEAICE. I'll go back to it. And Helen presented this case and they have grown EMFX data sets that were deployed over the last 10 years or more in the Southern Ocean, and I'll focus on 2 recent ones. Why do I have this here? It is, we've seen diagram kind of representing this. Interested into the turbulence here and different ways to measure it. Shear strength parameterization, which is what we can do with EMFX flows. Subscale and microstructure. So what I showed you before was microstructure, where you measured directly micro changes in here. It was in shear, but you can do it with several things. We're going to go back to EMFX floats. So they like outward floats, but measure horizontal velocity. From the velocity, you get the shear, and from the weakness, you get the strain, and you will show the strain. You can parameterize how much mixing you have in the wood column. So this is a data set from near the Finland Island. This is work that I did with my PhD. This is the trajectory of the memory 8 EMFX floats. And this is the parameterized mixing along the trajectory. And one thing from this figure is you have the plateau and rough topography down here, the current going from left to right for the XCC, the metallic cyclical current, and blue values is lower mixing and reds and yellows are higher. This is downstream from the plateau, closer to the topography, at the center of mixing, higher values. And we hypothesized that it was due to the generation of and dissipation of internal waves to generate heat. Now, Helen yesterday showed the mixing data from that study. Here I want to show you a little bit more about internal waves because we used the velocity profiles collected by the EMFX float, which are here, to identify individual features, covariant features or waves. So this is profile numbers in time over a few hours. It's U and V, and so you can see, I don't know how to see that. It's kind of a line. This is the most obvious feature. There is a pretty to be able to look at that meters of these things to try and identify by hand where I can see the features. And once I had identified these regions, I ran a series of did a lot of plots, and was able to get basically for each of these feature a few characteristics, including the vertical wavelength. So here's a map of where the features were along the tracks. In red, it was waves traveling upwards. In blue, traveling downwards. And a few stats on the left. I mean, I found down in this data set with an average vertical wavelength of 200 meters, horizontal wavelength of 15 kilometers. Something to see from the map here is first there was the front here and an eddy, so let's put more about it later. And the plateau, and you see that the red waves, the ones starting upwards, are closer to the topography and generated as the flow flows over the topography. Nicely illustrated here. A few things we looked into were what we call timescales. So dissipation timescale and propagation timescale. Dissipation timescale is how quickly you think the waves are going to break. How does it have to break? Kind of collapse based on what the genetic current. So we estimated that it was in the order of days usually. And the propagation is how quickly you think the waves are propagated by again, based on some characters. There's a few more timescales that we have, but these were the two at the time. But I was looking at a few more stats. We did find far more upward propagating wave in the polar front zone, which also happened to be because of topography. More energy in the front than in the polar front than elsewhere. Let's move on, because that's not the key point. This is what I'm interested to show today. So when you split your waves with the dissipation timescale, so the shorter timescale is whatever is going to happen first of the wave. So here we have dissipation longer. It's 120 times, 120 days here for this wave. Waves to break, dissipate. Propagation timescale, how long it will take before they move away. And so basically anything in this area here is more likely to dissipate locally, and the waves in the blue are going to be affected when they dissipate. And then they sort it by where they were. And so you see that a lot of the polar front zone and front internal waves tend to be affected by that part of dissipation. This was a few years back. Now more, and postdoc Ajita Syriac has been working on a bunch of them here, which is just south of Tasmania, south of Australia, Macquarie Ridge area, Meanders and Meander area. And she identified 112 waves in this data set. And here are some of the stats that go with them. But what's interesting is a lot more upward propagating waves. That's why. And I really want to focus on these timescales. So a few more timescales. We have a wave mean interaction timescale, like how long it takes for these waves to interact. Advection and wave mean, and advection, quadrant, and dissipation. So out of those 112 features, so each dot, cross, or circle is a feature, again sorted by where they were found in different types of eddies, front and polar front. And up and down, so circles is up and crosses is down, and it's a lot of information, but basically when you see that there's hardly anything, close to nothing dissipating locally. Not a lot happening just for the wave mean, but what dominates is really a combination of waves being affected and interacting with them. And so this points again in this area, we do have a strong front and jet, to the fact that the internal waves are more influenced by the wave mean interactions. Very few dissipate locally, and most of them are either advected away by the inflow or propagate away. And so I think I finish here saying that what we did observe most of mixing in the Antarctic signal current, and the characteristics of the internal waves are dependent on the and they tend to be advected away. And so really the flow, the front, the jets, or the meanders, whatever you want to call them here, they play a really important role in the evolution of the internal waves for advection and wave mean interaction, and probably energy and momentum, taking energy and momentum away from the generation side. So this is kind of a big unknown now into how do we parameterize or look at wave mean interaction and take this into account when we do the budgets. I think that was the last slide. Yes.